Okay, so it's rare that this happens, but today is what's known as a good news, bad news day.
Oh, great, it's a 50-50.
Okay? So the bad news is I have to spend the whole time explaining how these equations work and where they come from. The good news is you don't have any homework. Yay! So there's your trade-off. Okay? I'll try and make it as entertaining as I possibly can, but you don't have any homework. Alex?
I'm going to ask about how I would have done it. Number 13. I defined number 13 as time exercise.
There's no way of finding it. It's slowing down every single second, and then you speed up. There's no way to find it. Okay? You cannot, no, you cannot find it. That's it.
Oh, no, no.
Okay. So what we're going to do is this acceleration test coming up on Friday. And let me kind of begin to plant this seed. So you can get the test done in the allotted time, but you have to work efficiently. So if you're a fast test taker, you can get done. Okay, not a problem. But if you're one of those that goes, oh, I'm going to second guess myself for forever, okay, and spend 10 minutes on one question, then you might need to plan on staying after school on Friday. Okay, Mr. Hannon.
May I ask how many questions this test may have?
The numbers really don't matter because like one question might take up an entire page. Like there might be 5 or 6 parts.
So it's going to be like one A, B, C, D?
Yeah, it's going to be about half multiple choice and half big problems that you have to work out.
Oh, okay.
But I'll tell you exactly what the big problems are going to be.
Okay.
I will tell you on Thursday, I will tell you I'll even tell you where it's going to be on the test. Mm-hmm. Like I will tell you, this is going to be the last problem on the test. This is going to be the second to last
Where's the
problem on
rocket
the
going
test.
to be on the test?
All right.
Second to last.
The rocket question?
Absolutely. That's going to be the second to last problem on the test.
I just guessed it.
I have a severe schedule complication on Friday, and that I have to deal with them keeping move forward during first block.
We'll figure that out.
What?
Okay, so I'm just telling you, if that needs to be something that you need to keep in mind, like if you have to pick up siblings or something like that after school, you might need to make arrangements. You can't, like I said, you can't get the test done. But if you want a little bit more of a relaxed atmosphere, we're not going, wow, I gotta hurry, just might be something to keep in mind. Okay, so here's what we're gonna do. We're gonna go through these equations, and I'm gonna show you where they come from. I'm gonna show you under what circumstances you use them. And I'm gonna give you some kind of guidance along the way. So here's how the test is going to play out. On Friday, I'm gonna give you the test, and you're gonna have this yellow sheet of paper. And that's it, and your calculators, okay? That's it. So you've got to be able to use the equations that are on this sheet to solve the problem. Now, this first test is only going to involve the first 3 equations, okay? That's it. There's actually going to be a 4th one, which I'll introduce, because you need to understand that to get to some other equations. But that's it. Now, eventually, we're going to go through all of these equations on here. But for now, it's just the first 3. So, as we go through these, I'm going to give you some problem-solving advice. I'm going, hey, this is what I would do, this is what I would recommend. But here's one of the most important things you have to understand as we start to go through these. These are solving problems. This is not about getting an answer, okay? This is how can you think through a complex problem to figure out what information that you have, what information are you trying to find, and then once you sort through all of that, then you can say, okay, hey, this is how I'm going to approach the problem. So let me kind of explain how this sheet plays out with these equations. So if you look at this very first one, it says you've got Vx equals Vx naught plus Axt. Okay? So this is kind of this big formal equation. So let me explain why they have the x's on there. The x's are on there to reinforce the idea that when you have two possible dimensions for motion, a horizontal and a vertical, initially we're only going to deal with horizontal motion. On Wednesday we'll deal with vertical motion with gravity. And you'll hear me say this again and again and again. It's kind of like the ads in Vegas. What happens in Vegas stays in Vegas. In terms of dimensions, what happens in the x stays in the x. What happens in the y stays in the y. Okay? So the reason that these x's are there is it's reinforcing the idea to you that says, hey, if you have horizontal motion, your acceleration and your velocity in the x direction is the only thing that you consider. They could have done this for the y component as well. They could have said, oh, hey, I throw something up in the air like this, the only thing that's going to happen is what's going to happen in the y. Versus I take the stopwatch and I push it across the table, then I'm only going to be dealing with the x. So this just basically reinforces the idea that if you have horizontal motion, you only deal with horizontal motion. If you deal with vertical motion, you only deal with vertical motion. So typically, the functional version of this equation is just v equals v naught plus at. Okay, that's the functional version. So when you're writing out these equations and when you start to do homework and complex problems, you don't have to write out the x all the time. Okay, if you want to, if you're hardcore, you can. This is the functional version of this equation. Okay, so don't think you need to write that out all the time. If you don't want to, you can, but you don't have to. Now, I'm going to rearrange this just a little bit in terms, and I'm going to rewrite this as v equals at plus v naught. All I did was just rearrange it a little bit. Now, the reason I'm going to rearrange that just a little bit is to show you that all this is a slope-intercept form of y equals mx plus v. Okay? It's a physics equation hiding as a linear function. Okay? That's all it is. So let's say, for example, you start off and you have a velocity time graph that looks something like this. So there's 10 meters per second, there's 20 meters per second, there's 5 seconds. Okay? That's it. So here's the story. So the 10 meters per second, that's your initial velocity. That's your y-intercept. How fast are you going at the beginning? Okay, that's all it is. V naught is just your y-intercept, assuming that you're at time 0. The acceleration is your m value. That's just the slope of the line. Okay, that's all it is. Acceleration is just the slope of the line. You have time. That's graphed on your x-axis. There you go. Your y value is just, oh, that spun around. Your y value is just what your velocity is at the end of that time. Okay? So don't look at this and go, oh man, that's physics is tough. It's a slope-intercept form. Okay? That's all it is. Don't flip out. Now, here's the story. Harken back to this. When you deal with a velocity time graph, what does the slope of a velocity time graph give you? Acceleration. Now, here's the story. Thatcher, if I were to take this v equals at plus v naught and solve that for acceleration, what would you end up with? So I would have a equals what?
V minus v naught over v.
Okay? Now, all this is change in y over change in x. Okay? When you look at the acceleration being this way, all it is you're just finding the slope of the line. It's change in y over change in x. So don't flip out and go, oh, I'm finding acceleration. You're finding the slope of the line. Okay? That's all you're doing. Okay? Don't flip out. It's just the slope of the line. Now, here's the story. What are the only two possible signs you can have for that acceleration? Yeah, positive or negative. That's it. Okay? That's it. If you don't have an acceleration, guess what? You're not accelerating and you have constant velocity, and this is a horizontal line. Okay? Now, let me kind of show you how this plays out. So, Sydney, pick a number between 5 and 10.
6.
Okay? So here's the carrot car, and it's moving with an initial velocity of 6 meters per second. Alex, do you want it to speed up or slow down?
Slow down.
Okay? Braylon, pick a number between 0 and 4. 2 meters per second. So, and that took, I don't know, let's say 2 seconds. And what's the acceleration of the car? Okay? Now, so the other thing about physics is that every one of the problems you're going to have are word problems. If you hate word problems, physics is not your style. Okay? Because here's how I would play this out. I would say, hey, the carrot car is moving at 6 meters per second. 2 seconds later, it slowed down to 2 meters per second. Find the acceleration of the carrot car. Okay? So I would lay out this description in words. Okay? So if you hate word problems, it's going to get real ugly real fast. Okay? I'm just telling you, every one of these is basically a word problem. So basically, but then I just have to pick, is it a car, is it a rabbit, is it a ball, what is it? Okay, I just have to pick the option. Now, what some people like to do, and you don't have to do this, okay, I'm just showing you a potential problem-solving strategy. When you do these physics problems, there's 5 potential variables that you can deal with initially. V, V naught, and dat. Okay? So what some people like to do, again, you don't have to do this, but what some people like to do is off to the right, they're going to write this V naught dat chart, because it allows you to analyze what information that you have, what information are you missing, and what are you trying to find. Okay? You don't have to do this, but I'm telling you, if you get into these problems, like on tomorrow's assignment, and you read this problem and you go, man, I don't even know how to start this problem. If you don't know what information that you have from the beginning, you're dead in the water. Now, as we go through these equations, there's a couple of words of advice I can give you. One is the worst thing that you can possibly do. The test will be a train wreck. The worst thing that you can possibly do is read a problem and go to your equation sheet and go, oh, what equation am I going to use? Okay?
You don't.
If that's your first step, it's going to be a train wreck. Okay? You have to look at these problems in terms of a bigger picture. Okay? Now, the beauty of it is, start with this. What are my only 2 options that I can have on any acceleration problem?
You speed up or you slow down?
Speed up or slow down. In this situation, what's the car doing?
Slow down.
Now, Luke, what's the sign of the velocity? Positive or negative?
Positive.
Slowing down. So what do you know about the sign of the acceleration?
Has to be negative.
Has to be negative. If I do this and I don't get a negative acceleration, I have done something wrong. Okay? So, in this situation, your V naught is the 6 meters per second. Your final velocity is going to be the 2 meters per second. Distance, not part of the story at this point. I don't care how far the car has gone, not part of the story. Okay? Don't care. My acceleration is what I'm trying to find. And I know my time is 2 seconds. Okay? Now I at least know the hand that I'm dealt. Okay? Now I know the information that I have. And now I can start to figure this out. Now, a lot of times what I'm going to ask you to do is I'm going to ask you to draw motion diagrams. So if I ask you to draw a motion diagram for this, come in here and go, okay, here's my V1, that's 6 meters per second. So when I draw V2, Connor A, what are my only 2 options when I draw V2? I can either make it or smaller. That's it. That's it. That's all I got. When I draw V2, it's going to be bigger or it's going to be smaller? Which way is it going to go, Connor A? Smaller, because I'm slowing down to 2 meters per second. So then V2 would be something like this. V3, something like this. Now, Connor M. My velocity vectors are pointing to the right, and they're getting smaller. Which direction do you think my acceleration vector is going to point?
To the left.
And it's going to have what sign?
Negative.
Beautiful. So I know I'm going to have a negative acceleration vector pointing in the opposite direction. Okay? And all of this from the idea that I know this thing is slowing down. I haven't touched the formula. I haven't touched anything. All I've done is conceptually figure out what's going to happen. Now, Mr. Hanna, how can I show this situation on a velocity time graph?
If put the velocity, it starts at 6,
Beautiful.
and it goes down to 2.
And it's going to go down to 2. And that's going to take
2 seconds.
2 seconds. Cool. Now, here's the story. Charles, what's the sign of my acceleration going to be?
Negative.
Negative. So here's how you can, and again, the more ways that you can view a problem, the better off you're going to be. The better chance of success you're going to have. So Connor A and Connor M tag team and said, ooh, we're slowing down. The acceleration vector should point in the opposite direction. My velocity time graph also reinforces that idea because I'm starting with a positive velocity and I'm slowing down to a smaller positive velocity. So that should have a negative acceleration. I can't have one thought process going, ooh, I'm slowing down, but I'm going to get positive acceleration with positive velocity. That's awkward. Okay? Mr. Hanna?
Oh, no.
Oh, I think you had a question.
No.
Okay. So, now at this point, I've analyzed it in terms of vectors. I've analyzed it in terms of velocity time graph. I've analyzed it in terms of the information that I have. Now, I can move on to the formulas. So what you'll see is that, and you literally look at every answer key that I have. They all follow the same process. I'm going to start with this. I'm going to, okay, V equals V naught plus AT. That's my initial equation. I need this solved for acceleration because that's what I'm trying to find. So I'm going to have A equals V minus V naught over time. Again, you are trying to, I cannot emphasize this enough, you are trying to convey to me a process, just not an answer, okay? If I wanted answers, I'd have you all do this on a web program and I'd have you just type in the answer, okay? It's not what I want. I'm old school. I know you find that shocking. And I want to see your work. Now I know what equation that you're going to use. Now you can put in the numbers. Oh, final velocity. Cool. 2 meters per second. 6 meters per second, and that took 2 seconds. So check my math. That's going to be negative 2 meters per second squared. So step number 1, I can see the equation that you've used. Step number 2, I see the units and the numbers. Step number 3, I've got an answer. Hey, that matches. We said that should be negative 2 meters per second squared. It should be a negative number. It was. Life is good. Okay? Now, we talked about this before. Understand that acceleration is not how fast you're going. What acceleration is telling you is the rate at which your velocity changes. Now, if you want to, jump back up and go, I now know an acceleration of negative 2 meters per second squared. So, if I go over 1 second, how far down should I drop? 2 meters per second. Is that what happens?
Yeah.
I go over 1, I go down, I'm at 4, right? Then, if I go over another 1, I'm going to
2.
There you go. Got it right. Okay? if you like a monetary analogy, you have $6 in your pocket. You have to spend $2 per second. At the end of 1 second, how much money have you spent?
4 or 2.
You spent 2, so you have
You have 4.
$4 left. Another second goes by, you're going to spend another $2. Now, how long would it take, Mitchell, for this car to come to rest?
3 seconds.
Why?
Because you're taking 2 for each time.
Beautiful. And when the velocity reaches 0, you stopped. So I could have said, hey, how long is the car going to take to come to a stop? Well, then what would your final velocity have been? 0, and then that would have taken 3 seconds. Okay? Got the idea. Now, let's play the what if game. What if Alex had said, nope, I want the car to speed up.
Blitzkrieg.
And instead of being 2 meters per second, we're going to speed up to 12 meters per second. Okay? So what's the only thing that's going to change on that velocity time graph?
It's gonna go-
Connor S. Oh, sorry. Connor S. I'm still going to start at 6 meters per second, but what's it going to do?
The slope will be positive.
Yeah. So now that slope is going to go up like this. What's the sign of my acceleration going to be?
Positive.
Because I am
Increasing speed.
with a blank velocity.
Positive velocity.
Positive velocity. So now, if you come down here, then instead of taking 2 meters per second, I'm going to take 12 meters per second. Take 12 meters per second minus 6, divide that by 2, that would be a positive acceleration of 3 meters per second squared. Okay? Cool with that? Got it. Good? Grand? Okay. And again, I beg of you, when you start to do these problems, look at these from different perspectives. Just not, ooh, what equation am I going to use? Okay? All right, now, let's talk about a different situation. So here's the velocity time graph. And you're going to travel at some velocity, and then at some point later, you're going to be traveling at some other velocity. So you're going to go from V naught up to V. It doesn't make any difference if you speed up, slow down. I'm just going to have you speed up. Okay? So, now we haven't talked about displacement yet. This is going to be the next step. Okay? So, I need to find the area underneath that line. Why?
Because it's your initial velocity.
No. What's the area going to represent?
It's the displacement.
I want to figure out how far the car goes. Okay? We haven't talked about displacement yet, but we're going to. So, here's the story. I'm going to break this up into 2 areas. A lower area rectangle and an upper area triangle. Okay? So I've got this V naught to T, and then that V naught up there going up to V in that triangle. Matt, how am I going to find, what can I multiply together to find the area of that lower rectangle?
The time and V naught.
Beautiful. So this lower area here is just going to be base times height, which would be V naught times time. That's it. Okay? Cool. Now, the upper part is a little bit trickier. Jacob, how could I find the area of that upper triangle?
Half times the difference in velocity times time.
Ooh. So you're saying 1/2 the time, and then what?
V minus V naught.
Why?
Because you're not including the bottom portion, so it's just from where the triangle starts at V naught to the end.
Beautiful. So the height of this triangle would be V minus V naught. Okay? Cool. Charles, I want to find the total area, so what can I do?
Add them together.
Okay? So I'm going to take area 1 plus area 2. Not to be confused with area 51. That's a whole other story. So this is going to be V naught T plus the quantity 1/2 T times V minus V naught. Okay? Now, as you study science, chemistry, and physics in particular, good equations have a certain elegance to them. Okay? This right now is like the ugly duckling. Okay? This is such a horrible equation. Okay? It's so jacked up. But can we clean it up a little bit?
Yeah.
Tyler, could we clean this thing up? Like, for example, could I distribute that 1/2 T over V minus V naught? Okay, I can do that. And then I get 1/2 VT minus 1/2 V naught T. Now, Sydney, can I combine any terms?
Yeah.
What can I combine?
You have V naught T minus 1/2 V naught T.
Which would leave me,
1/2 V naught T.
okay? So then I got 1/2 VT plus 1/2 V naught T, right? Nothing magic. This isn't like sorcery. All I did was simple algebra. Now, at this point, could I factor out a 1/2? Could I factor out a time? Andrew's going, where we go with this? So if I did that, I would have 1/2 V plus V naught times time. Okay? Now, sometimes you'll see this written as V plus V naught over 2 times time. It's the exact same equation. Now, this equation is not on your big dog equation sheet. Okay? It's not. But don't look at this and go, oh, that's no, it's not. Let me show you an example. So here's the velocity time graph. You're starting at 6 meters per second, and you're going up to 12 meters per second. And let's say that that took 2 seconds. Now, could I do this? Could I just take 6 times 2, 6 meters per second, times 2 seconds, and go, I went 12 meters? Could I do that?
No.
Why not? I just did.
Does that give you 12 meters per second squared?
No, it doesn't. Seconds cancel out, I get meters.
Because it's only the rectangle, it doesn't include the triangle.
Oh! Now, if you do this, you're trying to use distance equals velocity times time. Okay? Distance equals velocity times time is a great equation. It's a great equation. But it is a one-trick pony. What's the only time you can use that equation?
When they have the same units?
When you have a constant velocity. What's the test on Friday going to be?
Acceleration.
Do you think you're going to use distance equals velocity times time? No! Unless I explicitly tell you, hey, the squirrel was running at a constant velocity. If I don't tell you that, no, stop, bad. Okay? And if you find yourself trying to use this equation, because it's like, Mr. Burkamp, I really like that equation, I'm kind of addicted to it. Have an intervention, okay? Get help, okay? Stop, okay? Nothing good is going to come from this. So if you ever find yourself just trying to take velocity times time, find a distance, stop. It's a train wreck. It's not going to work, okay? Don't do it. Don't do it. However, look at this. Let's just say, leave physics out of this. I said, look, I want you to find the average of 12 and 6. What would you do?
I would add them and then divide by 2.
So what would you get?
9.
9. So the average of 12 and 6 is 2. You added them together and you divided it by 2. So if you look at the average velocity between 12 and 6, that's oddly enough going to be 9 meters per second. So if I start at 6 and I end up at 12, on average, my velocity is going to be 9 meters per second. It's kind of punchy. Okay, cool, right? Now, if I tell you that you're moving at a constant velocity of 9 meters for 2 seconds, how far would you travel? Do not make this difficult. Huh?
18 meters.
18 meters. Oh, yeah, right. On average, I'm going 9 meters per second for 2 seconds. I'm going to travel 18 meters. Oh, but wait, there's more. So if you go into this, 1/2 v plus v naught time, then you're going to take 1/2 times 6 meters per second plus 12 meters per second times 2 seconds. So don't flip out and go, oh man, that's a weird equation. It's not a weird equation. What are you doing? Yeah, you're just, what are you doing?
Taking the average.
Yeah, you're taking the average of these two velocities. That's all you're doing. Okay? So where did that 1/2 come from? You're finding the average of two numbers. You add them together and you divide by 2. So what we're saying is, in this situation, on average, you would be going 9 meters per second. You're going to go 18 meters. Okay? That's all it is. It's like, oh, physics is hard. You're finding the average of two numbers and you're multiplying it by time. That's it. Okay? That's all you're doing. So you would travel 18 meters. Now, what if I said, hey, we're going to drive 6 meters per second at a constant speed for 2 seconds, and I want to know how far you're going to go. Could you use that equation, distance equals 1/2 v plus v naught, times time, under constant velocity conditions? Deacon?
I believe so, yes.
Why? I believe you're right, but why are you right?
Because your initial velocity is 6 meters per second, your final velocity is still 6 meters per second. So 12 meters per second divided by 2, 6 meters per second, you're going for 2 seconds. And multiplied by 2 seconds, you get 12 meters.
12 meters. Okay? So here's the beauty of this, is that distance equals v plus v naught over 2 times time. You can use that under any circumstance. You can use it with accelerated motion, and you could be speeding up, slowing down, doesn't make any difference. Don't think, oh, this is only going to work if you speed up. It works under any circumstance. So you can use this if you have constant velocity, or if you're speeding up or slowing down. But distance equals velocity times time, you can only be used under what circumstance?
Constant velocity.
When you have constant velocity. Okay? So stop that camera for a second.